Alright, so we have already seen what it means to say that a bounded function is Riemann integrable. And we did it through piecewise constant functions. We did not do it the usual way, that means using Riemann sums. We did, however, mention at the end of the last video that we are going to consider Riemann sums. And today we are going to consider Riemann sums. So let's see how we can relate Riemann sums to the integrability and Riemann integral that we have defined using piecewise constant functions. So let us first actually recall the definition of Riemann sums. This is something that those of us who are already familiar with integration theory know. Okay. So this is definition, and this is definition 11.3.9. Riemann sums. The beginning of almost everything here is same. We have a bounded interval and we have a real valued function with that interval as its domain. Let I be a bounded interval and if from I to R be a bounded function. Let P be a partition of I, because in order to define a Riemann sum, we need a partition besides having a function. Note that we are not saying that this f is piecewise constant with respect to this partition. F is just some bounded function on I and P is some partition of the interval I. Then we define the upper Riemann sum U of f for the partition P, or with respect to the partition P, which we denote like that, and the lower Riemann sum which similarly we denote like this, L of f comma P, by the following definitions. U of f, actually this is nothing new. Nothing new means for those of us who already have seen these things. Okay. In fact, actually almost all of us have seen this. I mean, in 12th standard school texts, we already have come across Riemann sums when we studied integration in calculus. So from there itself we are having this. A Riemann sum means it's a sum, of course. A sum where we have one term for each subinterval j in P, but there is a condition. We are assuming that this j is non-empty. P being a partition of I may have the degenerate interval empty set as an element, but we do not want j to be empty. We want j to lie in P, but we do not want j to be empty. It will be clear why we assume so. But what are the terms? The terms are these. Supremum of the set of function values where the input x varies over j times the length of the subinterval j, and in a similar manner we also define the lower Riemann sum to again be another such sum where again j varies over p and j is non-empty, and this time we take infimum of the function values as x varies over j times the length of j. So let us first see what these things are. You have a bounded function f on I and you have a partition p of I. F is of course real valued. Then the upper Riemann sum of f with respect to p is this sum. What do we have in this sum? In this sum, we have one term for each element j in p which is non-empty. Now note one thing, that because p being a partition is by definition a finite set, so the sum you are looking at is a finite sum. It's not an infinite sum. So there is no problem of convergence, non-convergence, those things are not there. It is a simple finite sum, so it's well defined and it has a real number value. However, we still have to be careful with this supremum. So what we are doing in each term, say you choose one j in p which is non-empty. Then you are looking at the supremum of the function values for the inputs coming from j. Will the supremum exist? That is another question, because this is just a supremum, right? And this is where boundedness of the function comes into play. Because the function is bounded on I, it will in particular be bounded on j, because j is after all only a part of I. And that's why the supremum will exist means will be a real number, but there is one more condition. J needs to be non-empty, because if j is empty, then the set of function values where x is coming from j will also be empty, and the supremum of the empty set is by definition minus infinity. To prevent that, we take j not equal to empty. So it's not actually enough to simply have a bounded function, but we also have to take care of this. Okay, so now at least we know that in each term like this, for each j in p where j is non-empty, this supremum is a real number. And we are looking at the product of that real number and the length of j. And length of j is of course another real number. So that's how you are getting the terms of this sum. And you take the sum of all such terms. Whatever you are getting as the value of this sum, that is the upper Riemann sum of the function f for that partition p. In a similar manner, we have the lower Riemann sum. Here also, if you drop this assumption that j is not empty, then if j is empty, this infimum will be equal to plus infinity. We do not want that. That is why here also we assume j to be non-empty. And the rest is similar. Okay, so this is upper and lower Riemann sums. And in fact, the very next remark, the next item, tells us just that. Why we need to assume that j is non-empty. So this will be remark 11.3.10. So the remark is just simply this: if j is empty, then the supremum of f of x as x varies over j is minus infinity and the infimum is plus infinity. If you want, you can write plus infinity or you can simply write infinity also. That's why we need the condition in the above definition. That is the reason. All right. So now how do we relate these upper and lower Riemann sums with the upper and lower Riemann integral? Okay. Because you see, so far whatever we have done, we have actually done in terms of piecewise constant functions. So you may be a little skeptical about this new integrability. You may think that, okay, fine, we have done something with piecewise constant functions, which is somewhat like what we do with these Riemann sums. I mean, how we usually go for integrability. But it may seem that like we are getting two different types of integrabilities. One, where we use this Riemann sums, which is our usual way, which is how we are taught about integrability in other texts. Here, however, we have used piecewise constant functions. So, are we getting something new? No, we are actually not getting anything new. We are in fact getting the same thing, same notion of integrability and same integrals also. So, the next two results are going to ascertain that. So, let us see what they are. The first one is going to relate these upper and lower sums with integrals of piecewise constant functions. And then in the second result, we are going to see that the two notions of integrability actually are the same. So, this next one is lemma 11.3.11. Again, the beginning is same. Let I be a bounded interval and if from I to R be a bounded function. Alright, so now we are going to bring in a piecewise constant function. Let G be a, let me write PC, okay, piecewise constant function, or okay, because I need to mention the partition, let me change it. Be a function let G from I to R be a function that is piecewise constant WRT with respect to the partition capital P of I. Not just that, it also majorizes F, that majorizes f on I, of course. Then the PC integral of G on I is greater than or equal to the upper Riemann sum of f with respect to P. Okay, so that's only one half of the statement, and the second half involves a minorizing function. If h from I to R is a function that is piecewise constant with respect to the partition. In the text we have P, but let me just take another one, Q, just to show that this is not related to this one. Partition Q of I that minorizes f on I, then I started okay, fine, I started this with let, here I have started with if, so I have to continue. Then the PC integral of h on I is less than or equal to the lower Riemann sum of f with respect to Q. So the interpretation of this statement is, of course, very easy. We have f as usual, and we have a majorizing piecewise constant function g, and g is piecewise constant with respect to some partition P of I. Then the PC integral of g is greater than or equal to the upper Riemann sum of f with respect to P. And similarly, we have this for the minorizing piecewise constant function h. That is fine, but there is something else about this result that tells us that actually upper and lower Riemann sums are better in the sense that they give us better approximation to the actual integral if the function is integrable. So what I am trying to say is this: you see, you recall the definition of upper Riemann integral and lower Riemann integral in terms of, obviously piecewise constant functions, because that's the only thing we know at this stage. What is the upper Riemann integral with respect to piecewise constant integrals of majorizing functions? The upper Riemann integral by definition is the greatest lower bound of integrals of majorizing functions, right? So whenever you take a function like g, which is piecewise constant and which majorizes f, at every stage its value is greater than or equal to the corresponding f value. Then the PC integral of g approximates the upper Riemann integral of f, but from above, because the upper Riemann integral by definition is the greatest lower bound, infimum. This is a better approximation. Why? Because it gives us, if you are coming from above and you are approximating something here, this is where the upper Riemann integral lies, and this integral is above that. this is either equal to this or it is below. That means it's closer to that level. So that is why the upper Riemann sums give us possibly better approximations. The exact opposite thing happens with the lower Riemann integral. When you think of the lower Riemann integral of a function, of a bounded function, then you are looking at integrals of piecewise constant functions that minorize the given function. That is, their graphs lie below the graph of the given function. So the piecewise constant integral of such functions fall short of being this one, this lower integral. And that's why we take the least upper bound of the integrals of this type of minorizing functions, and that by definition is the lower Riemann integral. Because this one, this lower Riemann sum is either equal to this or a little greater than this. So this is possibly a better approximation than this piecewise constant integral. So our usual way of introducing integration through upper and lower Riemann sums actually take us to the upper and lower integrals faster than these other things, the piecewise constant functions. And the reason also is somewhat, it should be clear. You see, using step functions or piecewise constant functions to approximate a possibly quite complicated graph, namely approximating f, using such functions is a very crude way of approximating, right? Whereas this is a better way. I mean, this sums. But if I just simply go on like this without doing actual mathematics, then it will be a wastage of time. So instead, let's just go ahead and state whatever we have here. I mean, if we go on talking like this without actually writing down any equation or anything, then you can just simply go on and on. So I just wanted to share some things about this thing. You see, this type of discussions also have their own importance. Sometimes you need to step away from exact equations, inequalities, and you think about those things in vague terms to some extent, so that you get a general idea of the things. Now that we have understood what's going on behind all these things, so let's now state the results. Oh, and the proof of this is one exercise. So this, of course, we will do in a community post. This is exercise 4. And now finally, we state this proposition, which shows that the two integrabilities, one in terms of these Riemann sums and the other in terms of piecewise constant functions, actually are the same. Let I be a bounded interval and f from I to R be a bounded function. Then the upper Riemann integral of f on I is equal to the infimum of uf, p, where p is a partition of I. And the lower Riemann integral of f over I is equal to the supremum of the set of lower sums, where again P is a partition of I. We know what these quantities are. Their original definition tells us, for example, this one is the infimum of the set of integrals of majorizing piecewise constant functions. It turns out to be the infimum of the set of upper sums as well. Similarly, the lower Riemann integral, which by definition is the supremum of the set of integrals of minorizing piecewise constant functions, turns out to be the supremum of the set of lower sums as well. So obviously, if you go back to your school definition of these quantities, upper and lower Riemann integrals, there these equations themselves are the definitions. Now, however, we have different meanings for this, and it turns out that we actually get the same thing back. And its proof is also one exercise. This is, I think, the fifth exercise. So that's just it. In this section, this is all we have. So once we solve the exercises, we will then be able to go to the next section. And in the next section, we will come across the elementary properties of Riemann integrals. We have already proved such properties for piecewise constant functions. But in the next section, we are going to prove those same things for bounded functions in general, which are Riemann integrable. Okay, so that's just it for this video. And tomorrow, what do we have? We have number theory. Actually, we have either number theory or class 11 mathematics. So let's do number theory tomorrow, and next Monday we are going to do class 11. Okay. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.